Hello everybody, welcome to GD50 Lecture 2. This is Breakout, and interestingly, CS50 has a history with Breakout, so I pulled this up today. This is PSET 3 in 2015, 2014. Was an implementation of Breakout using the Stanford Portable Library, which was a sort of Java library that we were able to get C bindings for. And so students were able to actually implement a game in what was at the time the CS50 appliance, which is a Linux distro. But suffice to say, that was oh, and a funny story also. I happened to also write the lasers for this implementation back in the day, and I think that was one of the first bits of code I got my hands dirty with when working with CS50. So today, in the context of Breakout, we'll be talking about a few different things that we haven't talked about yet, sprite sheets being chief among them most likely, at least the most visibly so. So sprite sheets are simply a way of taking an image, a large image, and rather than splitting it up, or rather than loading individual images for all of your different things in the game, whether it's your aliens, your paddles or whatnot, you can put everything into one sheet and then just sort of index into that sheet using rectangles, quads, we'll talk about soon, which will allow you to just draw a subset of that image and therefore condense all of your artwork just into one piece, one file. We'll be talking a little bit more about procedural generation in the context of Breakout. And in this case, we'll be laying out all of the bricks in the game world procedurally. So having, instead of the same set of colors, in this case, the standard layout is to have a bunch of the same colored bricks row by row. We'll actually implement a dynamic generation approach and have a bunch of different cool layouts we'll see, and it's actually quite simple to achieve pretty believable results. We'll manage state a little bit better in this game. So before, we sort of had a couple public global variables, and we didn't really have the concept of like a per state or a global state that we were cleanly sort of sharing between all of our states for our state machine. But to avoid having sort of like a polluted global namespace and to just sort of keep things a little bit cleaner, we'll end up taking all the important variables for our code, like the player and any other entities, the bricks, the ball, and rather than keep them in our main.lua, we'll end up shifting them. We'll sort of transfer them to and from the different states via the state machine's enter method. We'll actually have levels, so a progression system. So start at level 1, go up, and then with each level, we'll implement a scale in terms of the generation of the bricks. So we'll get higher tiered bricks and more points as a result. We'll have a health system, so hearts in a similar fashion to Legend of Zelda. Particle systems, which are a very important aesthetic component to 2D games and 3D games. Particle systems basically being a bunch of spawned images that you sort of cluster. You put into a little spawner, emit them in a certain way, and color them, perform math on them, and get sort of believable effects like fire and smoke and all these other things that would otherwise be sort of not easy to do using simple animation, but trivial with a particle system. We'll do a little bit more complicated collision detection with our paddle and with our bricks than we did with Pong. And then we'll also talk lastly about how we can save data locally to our computer so that when we close the application and run it again, we end up having a persistent high score rather than just something that's volatile. So first, though, I would like to demo today's finished game. So if anybody would like to demo from the audience, that would be nice. Go ahead and come up. Go ahead and queue it up for you. What's your name?
Jared.
Jared. Colton.
Nice to meet you, Colton.
Nice to meet you. So we're going to go ahead and run Breakout here. And so it uses the arrow keys. So if you go ahead and press up and down, you'll see you can move between the start and the high scores screen. So these are two separate screens. So go ahead and here we have, when you start, you can choose a paddle. So rather than just the same old paddle every time, you get to select. And as you can see here, he chose green, so he gets the green paddle. These bricks, all procedure generated, so if he reruns the application, they'll be completely different. And as is the classic formula, the ball moves between the bricks and the paddle. When it hits a brick, if it's of a certain color, it'll either get destroyed. In this case, if it's blue, it's the base color brick, so it's the lowest value. And if it's higher than blue, it'll end up going down a color, depending on which color it is. I believe it goes blue, green, red, purple, yellow. So anything higher will get shifted down. And then the player amasses points, as you can see top right, score. And notice also the 3 hearts, that'll be the player's health. So if he were to lose on purpose, possibly, we can see he gets another message that's saying press enter to serve. His hearts have gone down by 1, so now he's got 2 out of 3 health. And so eventually, if he were to, by chance, lose completely, oh. That's honestly the most fun part about Breakout, is just getting it caught in a bunch of stuff. But you can see we go to a game over screen, it shows your final score, and then you can press enter, and it'll, I must have had a bug. But that should take you back to the, in the event that you have a high score, it'll take you to enter a high score. And if you if you don't have a high score, it'll take you back to the start menu. So made a couple of last minute changes. Unfortunately, I must have left something in there. But that's Breakout in a nutshell. Our goal today will be to implement basically all the functionality we saw. Oh, we didn't take a look at the high score screen, so let's take a look at that really quick as well. So here at the title, you can see we have start and high scores. You click, oh man, okay, I must have screwed something up. So I'm going to go to Breakout 12. Okay, sorry, I apologize. I'm going to fix that, but it should show this menu here, where you will have a list of all your names that get loaded from a file and will output your score accordingly. And in the event that you get a new high score, you'll get to enter your name after that, and then it will end up saving it to another file. And when we get to that point, I'll try and fix it so that we can actually see what it looks like. So let's go back to these slides here. So this is the overall state flow of our game. So as you can see by me marking it out in a highlighted color, we start off in the start state, and this is all stuff we've covered before, just a state machine. It's a little bit more complicated than Flappy Bird, though. We have 1, 2, 3, 4, 5, 6, 7, 8 states, as opposed to, I think it was 4 or 5 in the last lecture. And the arrows illustrate which states can move in between other states. So as we saw, the start state can move via the up and down arrows in the high score state. It can move between the high score state and back. So when you go into the high score state, press escape, go back to the start state. The start state also has an arrow branching off to the left, going down to the paddle select state, where we saw the user is able to select a paddle to use. Once they've selected a paddle, we'll go to the serve state. They'll be able to serve the ball at their leisure, and then it'll go back and forth between the play state. So if they end up taking damage, the ball goes below the surface of the screen, they'll go back to the serve state again so they can reorient themselves. If they're in the play state and they end up clearing the whole entire set of bricks, they'll actually get taken to the victory state. And the victory state's where we increment the level, and we also regenerate the level. And then the victory state goes back to the serve state, and then we repeat that whole loop again. In the play state, if they are to get a game over, they'll go to the game over state, it'll tell them their score, and then they'll go to the enter high score state, depending on whether they have a high score. And if not, as seen by the arrow that goes up and to the left, they'll actually go back to the start state. And then the enter high score state will also go back to the high score state so that they can see, once they've entered their high score, their score relative to the other scores in the list. So in Breakout 0, which we're going to look at now, we're going to do some very basic stuff. So this is the day 0 update, as always. I'm in Breakout 0 right now. Yes, I am. So what we're going to do is I'm going to look at, first thing here, line 27. So before, what we were doing in our application is having basically a lot of files at the top level and sort of losing track of what we were doing potentially, especially as you start adding more and more files and you've got like 50, 100 more files. It's something that's obviously not maintainable. So the solution there, just put them in folders and then keep track of everything, keep them organized. And that's a major thing that we're going to start doing. And on top of that, we're also going to, in our code, keep things a little bit more modular. And that's why we have this file source/dependencies, which we'll take a look at in a second. We've allocated a bunch of global tables here. So we're taking the design decision of, even though I mentioned that we will be sort of taking a lot of the global variables out of our application assets, we're going to keep all of those in some global variables, and we'll see in the future how we can maybe implement a resource manager class that takes care of this for us. But for now, for simplicity's sake, in love.load, we're just going to have a few global tables that contain, in this case, global fonts. So by key, we can index small, medium, and large fonts, which are just new fonts at different sizes, 8, 16, 32. And we're using it, we have a fonts folder now instead of just keeping it at the parent level. We're going to set it to small. We have global textures, so background, main, arrows, hearts, particle. So we have the background, which was the background of our screen. Main has all of our bricks, paddles, the balls, etc. Arrows are going to be for the paddle select screen, the two left and right arrows. Hearts are going to be for our health. And then particle is a single small tiny little texture that we'll use to spawn all the particles in our particle systems later on as we get towards the end of the demonstration. So this is push. We're setting it up just like normal. Nothing new there, except the virtual width, virtual height, and all that stuff. Those have been moved out if we look into source in a constants file. So this file here, instead of having all of the constants in main, it kind of makes sense just to like take them out, put them in a file called constants.lua, and we can sort of manage all that. We can know immediately when we're looking at capital window width, window height, et cetera. These are all constants. If we have a constants file, we just can more easily track it rather than having to grep through all of our files to try and figure out what we were looking at. And the constants are used here in our setup screen as before. And then another sounds global table, just as before. We have a bunch of different sound effects. I've separated the music from the sound effects just so that we can see at a glance, oh, this is the music. These are the sound effects. Pretty straightforward. We have a state machine as always, and we're just going to use a start state for this demonstration. Setting it to start. Love.resize, love.update. These are all functions we've seen before, nothing too new. Love.keypressed. We have a global input table. So as in the case of Flappy Bird, we can index into that input table anywhere in our application and call love.keyboard.wasPressed key, which allows us to take input exclusively from main and use it in other modules. Here we're drawing so this is the actual rendering code. And we're doing this in our love.draw as opposed to a specific state, because this is actually going to apply to all states. We're always going to have this background. So rather than duplicate it over and over again, in this instance, this minor bit of code, we're going to display the background behind all the states. So all the states are going to render over this background and make it seem a little more cohesive. We're going to draw it at 0, 0 without rotation. And then this bit of math here, the virtual width divided by, and then background width minus 1, will end up being a scale factor so that we can always scale it to be our virtual width. Because the texture by default is some amount smaller than our actual window or our actual virtual width and height. But by dividing virtual width by whatever the background width of that image is by 1, we'll get a scale factor. Because virtual width is larger than the image, we'll get a scale factor on x and y that equates to it completely stretching to fill our virtual width and height. And recall that these two parameters are the scale on the x and the y. So it's going to be some like 1 point something or 2 point something, whatever it takes to end up filling the screen. And then lastly here, the new bit I implemented is just a display frames per second function, which I think is kind of important generally. And it's very easy to do. I don't think we talked about it yet, but just love.timer.getFPS. And then I just draw it in the top left in green so that we can see it throughout all of our iterations of the game, what our frames per second are. If you want to monitor without having to look through your terminal or anything like that, just displaying it at the top. It's standard practice in a lot of games. If you've gone to the debug console or whatnot, or sort of looked into some of the hacks, you'll see that in a lot of places. So I talked earlier about dependencies.lua. So this ties in as well to our effort to sort of modularize everything, keep everything organized. Instead of requiring everything at the top of main, let's just put it all in a file, and then we'll know at a glance what we're requiring, and we don't have to look through main and make main 100 lines, potentially a lot more than it needs to be. So requiring push, requiring class, same as we've done before. Require source.constants, so we have access to those. Require state machine, and then base state and start state. So let's go ahead and take a look at our start state. So I put states in a subfolder of source. This is another effort to sort of keep things modular. In this particular project, we won't have a lot of nested folders of code, but I decided to put the states in their own folder just so easily you can get access to all your states. So we'll look at start state here. On line 21, so recall in the start state, we just had breakout in the center of the screen, and then we had start game and high scores. So the user was able to highlight which state he wanted to look at. So we need to keep track of which one's highlighted. So all this variable's purpose is just to keep track. So 1 or 2, 1 being play game and 2 being high scores. And then here, if we press up and down, then because there's only 2 options, effectively, you can just flip whatever highlighted is with 1 or 2. If you have a list of options that's more than 2, then you'll need to increment 1 until it gets to whatever x is, your number of list options. And then if you press down at that point, you should flip back up to the top. And the same holds true for whether you're at option 1. You should go flip, rotate to the bottom of your list so that it looks as if you've gone all the way around. and then we're just playing a sound here when we do that. We have a love.keyboard.waspressed escape call here. It's not global anymore because there are some states in our application where we might want to press escape to actually go backwards, and we'll see that. And so rendering here, we render breakout with a large font. Now that we can access G fonts at large key in the center of the screen, set medium font, and then if we're going to render our two text fields one after the other, but if highlighted is equal to 1, then we're going to set it to some blue color, which is 103, 255, 255, 255, and then render it, and then make sure to reset the color after that. Because recall, Love2D is a sort of like a state machine in its own right, where if you set the color to something, whatever you draw and render after that, be it images or text, will adopt that color. So having everything be 255, 255, 255, 255, which is pure white, completely opaque, has the effect of drawing everything completely opaque. But if you don't do that, your images or whatnot that you draw afterwards will be tinted or transparent, which you most of the time don't want. But you might sometimes want that, and we'll actually see that in the paddle select state. And same thing holds true here. If highlighted is 2, do the exact same thing. And so if we run this application, which is mainly just a subset of what we saw before, we can move up and down between start and high scores, but if we press enter on any of them, nothing happens because we have no event handlers actually taking care of that. But we have the image scaled to the screen, we have breakout in the middle, and then we have our two menu options there. So breakout 1. So this is where we start to dive a little bit into sprite sheets, which is a major component of game development, 2D game development that we'll be looking at in the future and in this application. But a sprite sheet is just ultimately, rather than have, I don't know how many images there are on this sprite sheet here, but however many of these files, just have one file, put them all together, and then using rectangles define where the different sprites are. And then when we want to draw, use those rectangles and just tell love.graphics.draw, I want you to draw this texture, this sprite sheet, but I want you to draw just this section of it. You'd pass it in a quad, which is just simply a rectangle with height x and y. And Love2D will know, OK, I'm going to draw the image, but only this bit. And it has the effect of looking as if you're only drawing tiny little images as opposed to one monstrous image. And the functions that are relevant for us to look at are love.graphics.new quad, which takes an x, y, width, and a height, and also a dimensions object, which you get from an image. We'll see that. And all that basically is, I believe, is just an x, y, width, and height as well, or just a width and a height, rather, from whatever image you want to create quads for. And then love.graphics.draw, we've already seen it, but this is a different signature. This has texture quad x, y, quad being the second argument. And when it takes in this quad, it knows to only draw that defined rectangle of image to the screen. And so we'll go ahead and take a look now at breakout 1.
Are there any tools so you don't have to guess when you're doing the quad what the dimensions, like where it is on the sheet?
The question was, are there any tools so that we don't have to guess where the quad is when we're doing the sheet? Yes, there are, a lot of the time. I looked and saw a couple, but I haven't tested them thoroughly myself. For simpler examples like this, it's usually easy enough to programmatically do it. But yeah, when you get into having giant sprite atlases where you have, especially things that are not necessarily symmetrical or rectangular looking, even though they still need to be defined rectangularly, it's often best to use a tool like that. There are, I do believe, I just haven't used them. I can bring it up in a future lecture, and so we can discuss. Any other questions before we carry into breakout 1? All right. So I'm going to go ahead and open up the very first thing we should look at in breakout 1. In the source directory, we have a new file, and from here on out, we're going to always assume that when we introduce a new file, we're going to include it in dependencies.lua. And so in this case, all we need to do is just say require source/util, and as you can see, we're also adding a play state to this demonstration. But from here on out, I won't make mention of us actually adding it to our project. So util.lua is the module that contains the code that we're going to use to actually generate quads for a given sprite sheet. And this function, all it does is it takes what's an atlas or sprite sheet. The names are synonymous. You'll hear them both. Or we pass it an atlas. We pass it the width of the tile that we want and the height of the tile that we want. It's going to get the width and the height of the sheet here. So every image has a function called getWidth and getHeight. So we're just going to do that. And specifically, the sheet width and sheet height are the width of the image divided by tile width and tile height, so we know how many times we need to iterate over the sprite sheet to generate a rectangle. We're dividing it up based on the size of our tiles. And then we just basically do a simple nested for loop here. We start a counter and a sprite sheet. The sprite sheet is going to be a table that holds all of our quads. We just say for y get 0, sheet height -1, so starting at the top left going down, and starting at the top going down, and then x equals 0 starting at the left going right. At sprite sheet counter, which is 1 here, because in Lua tables are 1 indexed. We're going to create a new quad at x times tile width, y times tile width, give it the width and the height of our tile, so just whatever we passed into our function signature. Here it'll often be, in this case, be 16 by 32 because that's the size of the bricks. And then we pass in the last parameter that we saw in the slide, which is atlas : get dimensions. And then we just increment our sheet counter here. And then at the end of this, when we're all done, we'll return this. We'll have a table of quads that we can then use that are, sort of 1, 2, 3, 4, 5, 6, 7, 8. Well, I should say 1, 2, 3, 4, 5, 6, 7, 8, top left to bottom right of all the sprites in our sheet to make it super easy to look at. We have another function here. Lua doesn't by default have a slice function, but we are just adding to it, table.slice. It takes a table, the first entry in the table that we want, the last entry, and then the step between them. Just like Python's slice function, it just iterates over the for loop, which is first till 1, so 1 by default, until the last, or until the whatever this sort of number sign is the size of a table, which I don't think we've introduced yet. But basically this is, if we pass in last, it'll stop there. Otherwise, just assume we want the whole entire table. And then this comma here at the end, which has step or 1, you can pass in a step at the end of a for loop as a third argument, and that'll be however much it increments or decrements the loop that you're in. So by default, it's just 1. We go 1, then we go to 2, then we go to 3, but you can set it to -1. And so if you say for I gets 3 to 1 minus 1, you'll go 3 to 1, and you can't do a normally a step, which is what we do here. Or no, you can do a step, but you can't slice, which is why we have here sliced at number of slice plus 1 gets table I, and then eventually we return slice. So it just returns just a segment of whatever table we're in. And then the important function here that we're actually going to use in our application, we're going to generate quads paddles. And so this takes x and y, 0 and 64. And if we look back at our paddles here, we can see that we have various different sizes. So we have a small one, a medium one, a large one, and then a really large one. So if we want to get every single paddle in our sprite sheet, small, medium, large, giant, notice that we have 4 blocks. And within each of those blocks, we have 4 different sizes. So we can just iterate over this 4 times and then just define whatever the size of this rect is, that rect, and that rect. And we'll see the math for it here. If I go 0 to 3, for I gets 0 till 3, we're going to go ahead, because that'll give us 4. So that's how many times we want to iterate over the sprite sheet to get the separate quads. We'll get the smallest one. So quads counter, we initialize counter to 1, gets love.graphics.new quad at x, y, width of 32 and 16. Oh, and x and y default at 0 and 64 here, because recall that these are all 16 tall here. So we're starting y at 64, so that we start right here. And we're starting at x0, because it's on the left side. So we'll do that. We'll increment counter. Get it at 32 wide by 16 tall. Those are the actual dimensions of the smallest one. The same exact logic applies for medium and for large, only that we're adding 32, and then we're making it size 64. And then we're adding 96 to x at size 96 because they're getting wider, but they're also offsetting more to the right. And then the last bit is pretty much the same thing as before, except now we're going y plus 16 back to x because we've gone down a row in our sprite sheet. The paddle width at that point is 128, but still 16 pixels. And then here at the bottom, because we want to do this 4 times and we want to go through, the chunks are effectively 32 pixels because we're going 16, 16, 16, 16. We're just going to add 32 to y and then go to the next set of 4 paddles. So this is how we're effectively getting all of the paddle sprites, and they're going to be stored 1 through x, where I believe x is 16. So we'll have 16 quads defined in our sprite sheet thereafter that we can then return. So I'm going to go back to main.lua now. On line 64, here we have a new global table called gframes. We'll be able to access this anywhere we want to draw stuff. And it's just the same thing that we just saw, generate quads paddles, and we just pass it in our main texture. And our main texture is this. This is what our main texture looks like. And then we're going to index it. We're going to say it gets the key paddles because in that particular table was just the quads for our paddles. So in the future, we just need to call love.graphics.draw texture and then index into gframes paddles at whatever paddle we want, and that's how we can keep track of what we want to draw paddle-wise. And in this particular demo, we have a new paddle class because paddle is a thing in our game. We can represent it as sort of a class or an object. So we'll define a class for it. Everything's pretty simple thus far. It gets an x and a y. dx is 0, width, height, skin. The skin is going to be what color it is. We need to keep track of that. And then the size, because the size will be how we sort of offset into our paddles, our quads, because the sizes are small, medium, large, giant. 1, 2, 3, 4 times 4. So 1, 2, 3, 4 for the first set, and then 5, 6, 7, 8 for the second set. Those are all sorted by color. So we can just multiply skin times, or we can multiply whatever our size is by skin, and that will give us the current frame, the current quad that we want in order to draw to the screen. And then on line 7, so this is keyboard input here, stuff that we've seen before. If we're pressing left or right, then the paddle should move. The DX should be set left or right. We want to clamp it. We've seen this as well. Clamp the input to the left and the right side of the screen. If the DX is less than 0, do math.max and math.min. Otherwise, if we're moving to the right. And then here, this is actually where we tie it all together, and we actually use the quads to draw something onto the screen. So we're calling love.graphics.draw just our texture, our main texture, and then gframes at paddles at our current size, which is 2. We want to by default have the medium size, plus 4 times whatever our skin is minus 1. So if our skin is 1, we'll add, we won't add, which is the blue skin, we won't add anything to it. It'll just be 4 times 0. But if we have the next one, it'll be 2 minus 1, so we'll end up adding 4 to that. And because we're adding 4 to it times whatever that skin is, it'll just basically put us 4 quads in, which is the exact same paddle, but the next color. And then lastly, what we'll look at here is the play state. So we had just the start state before, but now we want to actually test to make sure that we can draw our paddle, move it around the screen. So we're going to implement a simple play state here. So on line 20, we're just calling self.paddle gets paddle. We're initializing a new paddle object. And then we're keeping track of also, this is a simple like pause demonstration. If self.paused, then actually, yeah, did I set self.paused? I do. OK, I just don't initialize it to anything up here. I should have set self.paused to false here. If self.paused, then we're going to test to see whether we're pressing space, and if we are, unpause it. Otherwise, basically just do the same exact thing in reverse. If we press space, pause the game, play a sound, etc. Here on line 39, we're just going to call update on the paddle, which just, remember, tests for left or right input. Here, we want to be able to escape the game, so we're just going to have a handler for escape. Render the paddle on line 47, which will do the love.graphics.draw with a quad, as we saw before, but it'll use the skin and the size of that paddle to index into the quad's tile sheet appropriately. And then here, if we're paused, let's just draw some text in the middle of the screen that just says pause, and we'll use the large font. So we can go ahead and demo this now and see everything come together. we have, as before, our start state. But if we press enter, now we go to our play state, and we just have a paddle at the bottom of the screen. It's size 2, skin 1, just the blue skin. And we can move it left or right, like that. And if it hits the left side of the screen, it'll stop. And if it hits the right side of the screen, it'll stop as well. So we've made progress, but this is one of the fundamental things I'd like to showcase today, is just like using quads and categorizing them, organizing them, and being able to draw your assets from a large compiled image rather than, keep track of however many images it would take, and you have to name all of them and sort them. It would just be a big pain. So yeah, definitely going forward, when you have more than one sprite, you want to sort of put it together in one sheet, and that's how we can accomplish that. But we don't have bricks, and this is probably the other big main component of Breakout besides the paddle and the ball. We want to have bricks that we can actually hit and aim for on the screen. So this update will address that. So let's go ahead and take a look at Breakout 2 in main.lua. I'm going to open it up here. On line 66, you can see we have a new table in our G-frames because we had one just for paddles. We took out just the paddles from our sprite sheet. We want to do the same thing for just the balls. So we're going to look at, if we look here, we can see that the balls sort of come after all of the bricks here, and they're just laid out in 8 pixels wide by 8 pixels tall little increments here. So 4 pixels to 1 brick, 4 balls to 1 brick, 2 balls to 1 horizontally, and then 2 balls vertically. And so what we'll end up doing is just a simple function in our util that takes a look at that. So let's go ahead and take a look at our util.lua, which we've made changes to. And so what this is going to do is sort of do the same thing that we did before. It has to iterate. So we have notice we have 2 rows of balls. We have these 4, and then we have these 3. So we want to iterate 4 times. We want to find whatever the offset is here, the x and the y. So it looks like 3 times 32, and then 3 times 16. So 96 by, I can't do math, whatever 16 times 3 is. And then we'll end up 48. And then we'll have, which is what we do here. So we have 2 iterations, so a for loop that goes from 0 to 3. So the top row, the 4. We'll set a counter to 1 here. Notice also 96 and 48, that's the x and the y that we're setting. That's where the offset is for the individual ball sprites. Quads at counter gets, and notice also quads is a table. We're going to return this. Quads at counter gets love.graphics.new quad at x, y, 8 pixels wide, 8 pixels tall. That's how large the balls are. And then we're going to add 8 to it because we're going to the right. So this iteration just goes left to right. And then here, we're going to do basically x being set to 96 and then y to 56. And then because we were editing x directly in here, we want to reset x back to 96, but then also add the 8 pixels so that we have the start for the next row vertically. So on at y, 56. Do the exact same thing here, but only do it 3 times because there was 4 balls on top and then 3 balls on bottom. And then return it at the very end. And so now we have just an individual table. We don't need to keep like one monstrous table of quads, which I find sort of disorganized. We can just have a table of frames for the paddles and the balls and the bricks, as we'll see. Actually, I have it up here, I think. Oh, maybe not. So in ball. Oh, actually, hold on. Sorry. So we were looking at. I skipped over this one on accident. So the bounce update. So everything I just said is relevant, but I accidentally hit right 2 times. We want to go to the bounce update because this is slightly simpler. So as we were just talking about the ball, which is perfect. So we're going to take the ball, and then we're going to add that to the scene, and we're just going to implement bouncing off the walls. So actually pretty identical to the code we saw for Pong, where you just detect whether the ball has gone past the left, right, or top edge of the screen. In this case, it'll also allow us to go to the bottom of the screen, and we'll also implement colliding with the paddle so we can get a sense of the actual gameplay and what that feels like. So everything is currently current. So we're going to go, after talking about the function to actually get the individual ball quads out of the sprite sheet, we're going to look at the ball class, which is going to allow us to spawn them in our scene. So a ball takes a width and a height of 8, no velocity, but we're going to allow ourselves to initialize the ball with the skin, and we'll see this later just as a cutesy little thing to use the actual individual sprites rather than just one constant sprite. We're just going to give it a random number between 1 and 7 because there are 7 quads, and then we'll just use G frames balls, that math.random number to get the actual ball sprite that we want. And so we have a simple collides function within ball, which will allow us to check to see whether we've collided with something that has a xy width and a height. So it's a simple AABB collision detection. And then here we have reset, just resets it to the middle of the screen. Update applies velocity, stuff we've already seen. This is where we actually implement bouncing off the walls. So if x is less than or equal to 0, greater than or equal to virtual width minus 8, or less than or equal to 0, this should be where we reverse the velocity. In the case of it bouncing off the left side, we want to reverse the x velocity, but keep it going up. If it hits the top, then we want to reverse the y velocity, but keep it moving in whatever direction it was moving. And same thing with the right-hand wall. And then play a wall hit sound. And we're incorporating the sound sort of as we go today just because they're so simple. And it's also kind of nice just to have a little bit of feedback when you're actually implementing the game. And the exact same code is here for drawing. So we have main texture, but now we're using gframes balls, and then we're indexing that at self.skin. And recall that we just set self.skin in here. So all we need to do to just make it random is just whenever we create a new ball, just give it a math.random 7, and then that'll index into that quads table. So we can draw a different ball texture each time. And so let's go ahead and see, oh, actually, no. And one last thing we need to look at is the playstate has a little bit of new code as well. We're going to spawn a ball. So this is where we do it here. I'm not doing it random, but I could do it random here. If I wanted to, I could do math.random 7, and every time we boot up the game, it's going to be a different color because it's going to be a different skin. We need to update the ball. So on line 50, we just update it like we do the paddle. And then on line 52, we're just testing to see whether it collides with the paddle because we're using just simple AABB. If it collides with the paddle, we can assume it was coming down. We can just reverse as delta y. Now, does anybody know what might be a current issue with the current implementation of this function, particularly with this line?
So if the ball is coming in from the side, then it wouldn't necessarily be bounced the opposite direction.
It will. You're on the right track. The answer was if the ball is coming from the side, it won't necessarily be bounced back up in the right y direction. If it's coming from the side, it'll always, in this case, be coming from up above, so it'll always still be reversing in the right delta y. But what's going to happen if it comes in at an angle and then isn't basically reset? Like, if currently right now, if it comes in at an angle and it gets like caught, let's say it's like below the top edge of the paddle, you're going to get an infinite collision loop because we're not resetting its position. We're only updating its velocity. If it comes in at the right angle from the side, it's going to get stuck inside the paddle, and then it's going to cause a little bit of funky behavior. I'll try and see if I can make that happen in my demonstration here. But that's the gist of all of these updates. So if we go to start, we can see immediately we have a ball, and then when it hits the sides or the top, it bounces accordingly. It hits the paddle, so when it comes in from the top, flush on the top, it flips the y velocity. Let's see if I can get it at an angle here. Oh, there it is. It'll get stuck. And so whenever you sort of do AABB collision detection, just remember to always reset the position of whatever it is that collided that's moving so that it doesn't clip and get stuck inside of something else over and over again. Yes?
So when you're running something, you're just doing love dot, and what I've been doing is like actually including the path to love that I get see. Can I just always keep love dot and I will run it?
The question is, I'm always doing love space dot, and as opposed to just running things from using the complete path of whatever the file is. In order to do that, so are you on a Mac or a Windows machine? So if you're on, on a Windows machine, it is a little trickier, but I found a really nice sort of plugin for VS Code. So if you're using VS Code, which is the editor that I use, it has plugins, and one of the plugins that you can download is for Love 2D, and it has a config where if you just press Alt-L, it will run your whatever directory you're currently in, whatever project you're currently in. It'll call Love. It adds it to your path for you. So download the Love 2D plugin on VS Code if you want that to work. I'm on a Mac, so I can edit what's called my bash profile and alias Love to its complete path in my file system. And you could do the same thing with, I don't know how it would work with Windows in terms of aliasing, but it's essentially the same thing as typing out the entire path to Love, but only I'm changing it to another word. I'm changing it to Love. So I'm setting Love equals to application/love.app/content/resources, etc. So good question. I would download on Windows. I'm a big fan of VS Code and the Love 2D plugin. I would recommend looking into that. And I'm sure there are other plugins, and there's a page also on the website. I don't have a browser open at the moment, but on the wiki, you can look at the Getting Started page. I believe it's like love2d.com/wiki/getting started. They have a bunch of instructions for different operating systems and different text editors that allow you to get sort of a more efficient workflow going. So, any other questions? All right. So we did the bounce update. Now we can finally edit the bricks. Add in the bricks, I should say. So these are pretty simple. So we're going to take a look at it. And right now we're not going to do any sort of fancy procedural generation. We're just going to get some bricks on the screen, just some easy bricks. Or rather, we will get some very basic procedural generation, but not to the level that we'll see soon. We'll see that very soon. OK, so I'm going to go into my main.lua here. I'm going to go into the breakout 3. And same thing that we did before. On line 67, we just have a new bricks table in our G frames. And it just generate quads bricks we call from util.lua. So we can look at that really quick as well. This one's actually really easy. Source util.lua. Because they start at the very top of the screen, we can assume that we could effectively treat this whole thing as if it were just these and just do generate quads at a constant width and height, because effectively we only need a subset of the frames it's generating. Because it's generating them this way, top to bottom, left to right, we can just grab all the way up to here using table.slice, which we saw before, and not worry about indexing into any weird, like having any constants x and y that we need to index with in order to get an offset. We can just do a very simple, if we go down to line 57, generate quads bricks. It just does a table.slice. And so within that, we're going to generate quads Atlas 3216. So this is going to have the effect of dividing up our sprite sheet by 32 by 16 pieces. It's going to generate all of these just fine, but then it's going to have quads here, 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 here that don't line up with the quads that you see here, because it's just blindly assuming that all of the sprites in that sheet are the same size, because it's all we're doing. We're just calling generate quads, which, if you recall, just generates a fixed size, width, and height throughout our entire atlas, which is great for a lot of sheets that are symmetrical, but there are cases where we have, like for example here, where our sprite sheet is asymmetrical. We have paddles of differing sizes. We have the balls, which are 8 by 8. We have the bricks. We have the other power-ups at the bottom. But the generate quads bricks takes in the table that we're generating, which is going to be a bunch of frames that we don't want, many of them clipped, half clipped. And then we're just going to take it from 1 to 21. And when we do that, 1 to 21 is effectively, that's how many of these there are. So 18, and then 1, 2, 3. So from 1 to 21, all of those, that'll be all the bricks. We can throw away all the rest of the quads and just blindly assume that they're all the same size. So any questions on how quads or how any of these tables are working? OK, cool. So we're going to go ahead. We have a new class now, brick.lua. So simple building blocks. In brick.lua on line 30, we have a flag called inPlay. Self.inPlay gets true. And so we're just going to use this to render it. We're just going to say, if it's in play, render it. If it's not, don't render it. It's that simple. That way we don't have to worry about object deallocation or anything fancy. We have all of our bricks, and whether it's in play or not, render it or perform update logic. And if it's not in play, just pretend it doesn't exist. Just ignore it. We're only going to have like 30, or I don't know how many, 13 max by 4 bricks in our scene at once. So worrying about freeing memory isn't really an issue. But if you have a million different things getting generated all the time, having simple in play is false might not always be viable because you need to store all that memory for all those objects. So just a shortcut here, but not necessarily best practice for very large games, but certainly great and simple for small games. On line 37, we define a function called brick hit. And all this does is just play a sound effect and set in play to false. And so all we're going to do is just check to see whether there's a collision, and then just call this hit function, play a sound, and then just pretend it doesn't exist anymore. And then all render does is if it's in play, checking the in play flag, draw main at bricks, or using our bricks table here that we created. And then we're going to start at 1, and then we're going to index it based on our color, -1 times 4, and then we're going to add its tier. So there are, if you recall, 1, 2, 3, 4, 5 colors and 4 tiers. And so what we're going to do is we're going to jump between the colors. So we'll go value 1, value 2, value 3, value 4, value 5. That'll be our first 5, or I guess 6. That'll be our first 6 bricks. And then we're going to go 1, 2, 3, or we're going to have a tier basically. It'll be 1, 2, 3, or 4. And if it's at tier 1, then we can just add, basically to index into whatever tier we're on, we just need to add tier -1 to whatever our index is. So here, if our tier is 1, then we just want to render this block. We don't want to go to the next one, so we're just going to say tier -1. We're going to add, so tier 1 minus 1 is 0, so we're going to add 0 to this, get this. But if tier's 2, we'll add 1 and 2 and 3. And then we just multiply whatever brick we want by our color, multiply it by 4 to get an offset for whatever our actual color is. So we take our color, figure out where in the sheet it is, and then just add our tier to it in order to index into our sprite sheet accordingly. And so that's what the math here is doing. And if we go back to our play state, and I'm going to start moving a little bit faster just so we can keep caught up. But in our play state, one thing that we notice here, we have a new class called Level Maker that we're seeing, which has a function called create map. We're going to take out all the logic for generating our levels, and we're just going to put it in one place. We're going to call that Level Maker. Rather than in our different states that maybe generate the bricks, like the play state or this, I guess it would be the serve state, victory state, I guess. Rather than generating all the bricks in that state within its init code, let's just make a level maker, and we can just say, okay, set bricks to levelmaker.createMap, which will return a table of bricks. Same logic as we saw before. In this case, we're just going to iterate for k brick in pairs of self.bricks. If the brick's in play and it collides, if the ball collides with it, then hit it, which will set it not into play. So simple AABB. And then lastly, we have our render logic here. We're just going to take that bricks table and just iterate over it. And the last thing we should probably look at is the actual level maker itself, which in this case is very simple, but we'll see it gets a little bit more complicated later when we have a very a more elaborate procedural generation approach to our levels. But right now we're just going to say set 2 random variables here, number of rows and columns, and then for every row, or for every row and then every column, create a new brick. And then there's some math here. I'm going to kind of skim over it, but basically it calculates where the brick is and then gives us 8 pixels of padding on either side. And then based on how many it is, it needs to center all the bricks and shift them by a certain amount to the left and then start drawing all of them. And that's essentially what this code does here. So calculate the center, I wrote it out in comments here, but I'm going to kind of glaze over it for now. But effectively, center all the bricks. Basically, calculate what offset on the x-axis you need to put all of them so that they appear centered. And then you're just going to draw them all out. And then that's it for the level maker class. So simply number of rows and columns, and then fill a table with bricks, but set their x equal to however much we need to center all of them when they're all drawn out. So we need to basically take in our number of columns into account when we do that. And then if we go into breakout 3 and run that, we have bricks. They're getting collided with, and as soon as they get hit, collided gets set, or in play on each of those bricks gets set to false, and they no longer get rendered. And they no longer get updated in terms of collision. Now we still have the issue with the ball not getting reset. We'll fix that. That's an easy fix. But we're coming a long way. We have things moving at quite a pace. I'm going to go ahead and move to the next bit of code here. So this is another bit of code. I'm going to sort of glaze over a little bit of the details here. But at a high level, what we need to do is, it's one thing to detect that we've collided with a brick, but in breakout, the ball bounces off of the brick depending on which side it hits. And we don't know this necessarily just based off of the collision. We just know whether the collision is true or not. We don't know where it came from and how much it collided with. And then we're also going to fix our paddle so that rather than, because currently all it does is just negate whatever the y velocity is, but we want to add a little bit more variety to how we end up sort of ricocheting the ball off the paddle when we play, so that we can sort of strategize a little bit, give ourselves a little bit of gameplay. So if we are moving to the right and we hit the right edge of the paddle with the ball, it should probably go in a sharper direction. Same thing with the left side. And we can effectively do that by taking the middle, figuring out how far away from the center it is, and then just amplifying our delta x in the negative or positive direction based off of that. And that has the effect of causing that to happen. So here we can see we have the ball sort of coming at the paddle, and let's pretend that the paddle is moving to the left. In this case, however far away the ball is from the center, we want to scale that by some amount and then end up making that our negative delta x, because that's effectively how the game normally works. If you move the paddle to the left or the right, hit it on a corner or something, it gives it that sharp angle, and that's effectively what the sharp angle is. It's just a strong delta x, and it gets amplified the larger this is. So just basically take this, multiply it by some amount, and then make it negative or positive on your dx. That's your sort of paddle collision v2. Brick collision is a little bit, it's pretty simple, but it's a little bit more complicated. Basically, what we need to do is just check and see which edge of the ball isn't inside the ball, inside the brick. And so if the left edge of the, and we can also sort of simplify this a little bit. If the left, as you see here by the pseudocode, if the left edge of the ball is outside the brick and the dx is positive, then we can say, oh, we can basically assume, oh, we've come in from the left side, so we should probably go in the opposite y direction on the left side. We should go in the same y direction, but negate our delta x, because we're coming in from the left. The left side is outside the brick, so bounce it back. And the same thing for the right edge. And we only need to do this test, the left edge of the ball, if dx is positive, because if dx is negative, there's no way the ball's colliding with the left side of our brick. So we can shortcut that effectively. We do the same exact logic here, just on the right edge of the brick instead of the left edge. And then if none of those hold true, we're going to see if the top edge of the ball is above the top edge of the brick. And if that's the case, we know that we've hit from the top. We can trigger a top collision. And if none of those have held true, we know that we have had a collision of some kind. We can just register a bottom collision. And so this is a simple version of this sort of way of doing breakout collision. It has a few faults when it comes to corners. Sometimes corners can be a little bit finicky, but I would say it works 99% of the time. For a much more robust and better example, I would look at this URL here, because he also goes into a full sort of breakdown of how he would implement Arkanoid, which is the same thing effectively as breakout, if you just want an alternative look at it. But basically, his solution involved taking how much the x and the y differed on different points of the bricks relative to the ball. And I believe he also kept the ball as an actual ball with a center point, even though he rendered it as a as a rectangle. So it's a little bit more robust. I decided to implement a simpler way, which I'll showcase, which is the way that I demonstrated, because it worked well and it wasn't too much code to sort of look over. But I do encourage you to take a look at that. We're going to look at our play state now in breakout 4. And in our play state, we're going to see, line 65. So this is the actual paddle code for influencing the ball's delta x. So basically, if the ball dot x is less than the paddle dot x plus its width divided by 2, so basically on the left side of the paddle, and the paddle's delta x is less than 0, which means it's moving left, because we don't really want to necessarily influence it if we're just standing still. We're going to do what I described earlier. We're going to give it some scalar, like some start-off value, in this case negative 50. It's just a sort of seeding this, giving it some sort of initial value. And then we're just going to subtract the ball's x from the middle point, this being the middle point of the paddle, and then just multiply it by 8. So whatever the difference is between the paddle, or between the ball's x and the middle of the paddle, multiply it by 8, add it to negative 50, and then negate that whole value so that the whole entire value becomes negative. And we therefore get a sharper delta x depending on which angle it's come in at, and also how fast, or not how fast, but whether or not we're moving left. And it's the exact same thing on the right side, only because we're taking this math, the self.paddle.x plus self.paddle.width divided by 2 minus the ball.x. The ball.x is going to be greater than that point. So this value is actually going to be negative. So we're going to just make it positive with math.abs. So absolute value, just a Lua function. So the absolute value of the difference between the ball's x and the middle point times 8, add it to 50. And that'll give us a positive value that scales depending on whether or not we've hit the middle of the we've hit the right edge of the paddle and are moving to the right. And so that's, in a nutshell, how we get the collision to work with the paddle, and how we can tweak delta x to be scaled a little bit more than just a constant, negative, or whatever its current x was, but negative dy, a little bit more complicated. And then the actual collision code for the bricks themselves is going to take place in a for loop here. So if it's in play, if the ball collides with it, hit it. So I added +2. So the gist of the math is if ball.x is less than brick.x and the ball's moving to the right, self.ball.dx is greater than 0, then flip its x velocity. So bounce it to the left. That's what this check is. But it plays a little bit rough with corners, because you could theoretically get into a position where you come in at an angle and then it's intersecting with the paddle in 2 positions, both on top and the left, or on bottom and the left. So in that case, adding 2 sort of prioritizes the y being hit. So it basically takes the check from the x position of the ball to the x plus 2. And so it ends up fixing the corners a little bit. But the gist of it is just check to see if the ball.x is less than the brick.x. And if it is, and we've detected a collision, we can bounce it. So there are some subtle corner case bugs without adding this +2. So we add that. And then flip the velocity here. This shift here. This is what we were talking about earlier with make sure when you do a collision, shift whatever is moving outside the boundaries of whatever you're colliding with. So self.ball.x gets brick.x minus 8 because the ball is 8 pixels wide. It should actually be self.ball.width for better style, but that's essentially what it translates out to. Same thing for the right edge, the +6 because it's on the right side, so it's effectively the same thing as -2 if we're on the left side. Just sort of fixes corners, weird issues with corners. But checking to see if basically the ball plus its height, -2, is greater than the brick plus x plus brick.width, which it means, we've collided with the right edge of the screen, of the brick. And then if the y is less than the brick.y, then we've collided with the top of the brick, and otherwise we've collided with the bottom. And with the top and the bottom, just do the same thing we did with delta x, but do it with delta y, but you're still resetting it. So ball.y gets brick.y minus 8, ball.y gets brick.y plus 16 because the paddle, or the individual bricks are 16 pixels tall. That's the gist of the collision detection. And then if we actually, oh, and one other thing that I ended up putting here just to make it a little bit more interesting, and this also ties into more complicated collision detection. If your velocity is too fast, a lot of the time it'll skip through objects. And then that causes a lot of problems with these collision detection functions that normally are very sort of mathematically correct and they work well. They don't work well when it skips over what you're trying to actually collide with. So a solution to that, which was beyond the scope of this example, but something worth thinking about, is perhaps stepping backwards a certain amount of time, a certain amount of pixels, perhaps maybe start at where your ball was on on the last frame, and then just add its width and height to itself until it collides with something, until it reaches whatever its current delta x or delta y plus its position is. That's one way to do it. Sort of just adding a bunch of invisible, whatever you're colliding with or whatever you're using to collide, add a bunch of invisible those to bridge the gap and check until if any of those hold true for a collision. A little bit more computationally expensive, but a lot more accurate in terms of the physics. And aside from that, everything is the same. So if you look at the code in Breakout 4, and I'm going to go a little bit faster henceforth. That's probably the meatiest part of the program. We get collisions. And then I'll try and get a strong angle so I can demo the... that didn't work. That actually gave a weaker angle. So if you do this and you do it close to the center, it has the opposite effect. But there we go. That's a sharper angle. So now you can actually influence the ball in a little bit more of a personable way, and not just have it be a flat delta y gets negative delta y effectively. So any questions on sort of how the gist of all of that works? Okay, perfect. So now we're going to get into a little bit more of some fun stuff. We'll do a couple more examples, then we'll take a break. So this is the hearts update. So notice that at the very top of the screen, as I've demonstrated in these slides, we have just a few hearts. One of them is empty. We showed this earlier. And then we have a game over screen, which shows us our final score. So I'm going to go ahead, and we're just going to look at the code a little bit faster now, since a lot of this stuff's fairly straightforward. I'm going to go ahead and open up I'm going to make sure I'm in the right folder. First of all, Breakout 5. And then in the... So one other thing we're going to start doing is, I mentioned this earlier, and it's going to hold true for any of the sort of state transformations that take place going forward. Rather than keep global variables, we're going to sort of do away with that idea outside of the asset tables that we have, just because those are kind of an exception and they could reasonably be put into a separate class called a resource manager. We're going to have we're going to start passing in what is basically our current app state, or at least the variables that make sense. And this is a common paradigm in web development with React as well. But basically, everything that we need to preserve state to state, rather than just keeping global variables, let's pass them between the states, because the state machine allows us to do that in the change function. And then whatever that state is, in its enter function, it'll have access to that. And it can just set those values to self.whatever and use them. But we no longer have global variables. We're just saying, here's the values that are important for you to continue on. And then that state will take its values and go to the next state and say, oh, OK, here are the values that you need to function. Like the serve, play, and all those states that have the core gameplay involved, we'll probably need to maintain a reference to the paddle and to the score, the amount of health we have. But when we get to the end, for example, and then we no longer really need a paddle, we no longer really need bricks or anything like that, we just need to know what our high score is so that we can enter it into our high score list. All we really need to do is just pass in the high score state entry, or just our high score, and that's it. So it encapsulates all of our data, and at a glance we can sort of see what we need to pass between the states and what's going to be relevant at a glance as well. It just cleans things up quite a bit. So that's what we're doing now on line 35, and henceforth we will do this in every state as we see, but I'm going to sort of glaze over it in the future. We have a serve state now. So a serve state, this is very identical to what we did in Pong. So we just wait for the user to press space. They can move around. And then when they do press enter, basically the ball starts moving. And then we change the play state here using the current values that are necessary. Paddle, bricks, health, score, and ball. Those are basically the fundamental variables that we need in order to keep track of our game state. So we have a serve state. It'll wait for us to press enter. And then our main.lua, we have a new hearts table. And then on line 208, because we're going to need the ability to render health and render our score across several states: play, serve, victory, game over. Actually, not game over, but the three before that. We don't want to duplicate this behavior, so I'm just calling a function called render health, which just takes in whatever our health is, and then we just set an x to virtual with minus 100. And then for however many health we have, draw a heart from the hearts sprite sheet, which I separated the hearts out into a smaller image, so you can just split them on like 8 by 8 or whatever it is. But just draw those and then add 11 to x, and just keep going until we've drawn out however many hearts we have. That'll draw full hearts. And then 3 minus health will give us however many health we're missing. So if we took a point of damage, this is going to be equal to 1. So then it'll draw 1 empty heart after that, or it'll draw 2 empty hearts. So draw however many full hearts we have, then draw the empty hearts. And those are 2 separate sprites that we get from the image. And that'll have the effect of drawing our health. And then our score is simply, it takes a score variable that we pass into it here. And also note that the render health takes in a health variable that we pass into it here. And so in our play state, we are calling both of these functions on line 135. On line 135, we are calculating whether we go below the edge of the screen, which is another important part of the game. Obviously, we need to detect when we've lost health. So it's as simple as this. If it's greater than the virtual height, decrement health by 1. If it's equal to 0, change to game over. Else change to the serve state. And note that we're passing in all these variables to and from our states, the ones that are important. Game over just needs score, but serve needs whatever variables we were already using. And then down here, we're calling render score and render health. And then the game over state is simply, because it takes in score from the parameters list, just wait for keyboard input to go back to the start, and then render game over. Here's your score. It's self.score, and then that's it. Very simple state.
Just a quick question.
Sure.
So any of these states have access to its parent file?
The question was, do any of these states have access to their parent
So
file?
that you're calling something from main.lua, so it has access to everything in main.lua. This is essentially global.
Is everything in main.lua global? Functions, yes.
Okay.
Functions that you declare. Anything that's basically not specified as local that you define in main.lua will be accessible anywhere in your application, including functions.
You don't have to declare it as public or anything? Or?
You don't have to, the question was, do you have to declare it as public? No, there is no notion of public. In Lua, anything that does not have a local specifier is assumed global, even if it's in a nested scope. So you could have a for loop. You could have several nested for loops and declare some variable without local. That variable can be accessed anywhere above it or outside of it. So it's pretty important to use local variables when you're not explicitly allocating something as global, just to avoid the bug of for nested loops in, you have some variable named like hello, and you use it somewhere else. Good questions, though. So yeah, we have a bunch of states now. We have a game over state, a play state. We're rendering our score, rendering our health. If we go and take a look at breakout 5, is it in a different window? There we go. We can see hearts at the top, score 0. Oh, and I forgot to mention the part where we actually add score now. So the bricks themselves in their on hit, or I should say in the play state, on line 81, when we detect a hit, we're just adding 10 to the score for now. But later on, we'll do a calculation where we take tier and color into consideration and then perform arithmetic on that to get our total score for each ball hit. But yeah, we're generating, we have our health, we have our score, and then once we take enough damage, we'll end up going to the game over screen. The game over screen will go back to our start screen. So making progress. And then probably my favorite of the updates before we take a short break is the Pretty Colors update. So what this does is clearly we can have, we've updated our level maker. So rather than just having a bunch of very static bricks, we end up doing a little bit more complicated procedural generation. It's not complicated though. It just in levelmaker.lua in breakout 6, we have a few different constants here. So solid, alternate, skip, or none. I actually don't think I use skip or none, just solid or alternate. Basically, we have flags now. So number of columns, and we ensure that it's odd because even columns with generating patterns leads to asymmetry. So make sure the number of columns is odd. Generate a highest tier and a highest color based on our level. So in this case, we'll go no higher of a tier than 3 because we have no higher tiers than 3. We go 0, 1, 2, 3. And then whatever our level divided by 5 is, and then we just take math.floor. Math.floor takes in basically performing division and then truncating the decimal point. Well, not division. It just literally truncates the decimal point off of a number. So level divided by 5, whatever that is before the decimal point. Level modulo 5 plus 3 for the highest color. So we'll cycle. We'll go over and over again, go highest color, 1, 2, 3, 4, 5, and then we'll go to a new tier with level divided by 5. So basically every 5 levels we'll increment in tier, and then we'll start back at blue, and then go on and on and on like that. For every number of rows. So basically I have a few. I'm going to sort of glaze over this a little bit just because we're probably going to run short on time. But we have basically 2 flags, whether we're skipping bricks in this row or alternating bricks color-wise. And if we do, we need to set a color for it and a tier. And then we basically just say, the same sort of logic that we had before where we generated random rows and columns. But if we have the alternate flag on, then as we can see in some of these photos here, here we have skip is true. So the color for that row is set to the blue, but skip is true. So every other brick, it's just going to skip that iteration of the loop. Same thing here, only it's offset by 1. Same thing here, same thing here. So this is kind of a nice little pattern. And in each of these cases, or actually not each of these cases, notice this third one, it also set alternate to true. So it goes green, purple, green, purple, green, purple. And so the logic there is if alternate's true, then just flip the color every iteration. If skip is true, don't generate a brick every other iteration, and so on and so forth. And then if you have solid, then, or if you don't have alternate equals true, then you have a solid brick like these blue ones. And if you have if you have alternate but no skip, you get this sort of pattern where you have green, purple, any random color. And then also the number of columns is random, so it can go, here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, but on this very bottom one, we have that minus 2, it looks like, because it only goes that wide. And so, and notice here too, smaller size, that one there's no spacing. So these are very simple concepts, like just, should we skip a block this iteration? Should we alternate the colors? And when you put them all together, it produces things that look as if they were almost handcrafted. Like this could be made by somebody, like that looks like it was made by somebody. Pretty much every iteration of this, I mean even that looks like a shape almost. It's just very simple, but the results are pretty awesome in my opinion. And so that's just the gist behind what we're doing. We're just setting flags and just saying, if we're skipping this turn, then just every iteration, every time we lay out a brick and we spawn a new brick on this row, just do or don't. Just make its color, pick 2 colors if we're alternating, and then set its color to whatever the off color is that we're alternating. And if we're skipping and alternating, then we're just doing, whenever we're on a brick that we're actually laying is when we change the color, the alternate color. And so, like I said, I won't go into too much detail. Happy to talk about the generator after class, but just because we're running short on time, sort of going to wave my hands over it, but that's it in a nutshell. So any questions before we take a break for 5 minutes? Yes?
When you detect the ball in the brick, if the ball was so fast that it was
The question is, in an instance with this programming, if the ball were so fast that it were actually inside the brick, would it what?
Would it still bounce back?
Would it still bounce back? The answer is no, it wouldn't. This implementation doesn't take into consideration velocity that goes too fast. Mainly to introduce, for two reasons. One, it's non-trivial to implement, and two, it's an interesting thing to look at and observe and be conscious of as you go forward in implementing your own games. The current code, if it gets clipped inside of the brick, it will have no edges that are peeking outside of the brick, and therefore it will default to the final condition, which is the last else clause, which puts it below the brick. So it'll just go below the brick. It'll almost be as if it came in from the underside and bounced out. But like I alluded to earlier, if you wanted to implement something like this yourself, you would have to slice up frame x and frame x plus 1 into the size of the ball if the delta is so wide that it either goes inside of a brick or it goes outside of a brick, or if it skips a brick. And this sort of solves that problem. It solves both of those problems, but it's a little more than we can cover in this example. Any other questions? All right, let's take 5 and get back to it. All right, and we're back. So the next step is we have basically a layout dynamically generated of interesting bricks now, but we haven't really implemented scoring any of these. We just have score gets score plus 10, which isn't really particularly interesting. So breakout 7 is what I call the tier update, which should allow us to hit blocks that are of a higher tier than just base blue. And if they are of a higher color than base blue, they should go down a color. So the hierarchy was, if we look back, blue goes to green, goes to red, goes to purple, goes to gold. And if something is a higher tier, it goes to the next color below it, but at that same tier. Unless it happens to be like blue and gray, and then in which case it'll go back to blue. So how might we implement scoring based on this system? What do we need? What pieces do we need? What pieces do we already have that we can use to make this happen?
The brick index, right?
I'm sorry?
The brick index, right?
So-
So there are these 7 different kinds of bricks, right? So if you know where it is in the hierarchy, you can, and the current score, you can do multipliers based on that.
So the answer was the brick index. So yes, the brick skin and color are the pieces. Yeah, so those are fields of brick. So if we open up, I'm going to go up to breakout 7, and I'm going to start probably deferring a lot of this code to future reading. But in brick here, the tier and the color, sorry, not the skin, but skin is for the paddle. But the brick has a tier and it has a color. And so we just need to perform some arithmetic on that here. And that's essentially what lines 44 through 58 is. So basically, oh, I apologize. That's not actually where the arithmetic is. 44, that does compute, but this is the bit of code that computes how we can actually go backwards if we make a collision. So if we collide with a brick and it's of a higher tier than 1, and it's a higher color than blue, it should be brought back one step. But if it happens to be blue, in which case self.color gets 1 because blue is 1, then it should just be removed from play, just like we've done before. Only now we're also taking in tier and color. So we're decrementing tier based on what index we're at, and we're decrementing color. And then this actually gets used in our play state. If we go to line 81, which previously just had self.score gets self.score plus 1. There's a little bit of math here. It's very simple, though. Just brick.tier times 200. So I'll make the tiers worth 100, plus brick.color times 25. And so if tier is 0, if it's a base, then we're just not going to get that 200 bonus. But the first tier, everything's going to be worth 25 times whatever its color is. So 1, 2, 3, 4, 5. And then add 200 plus the brick.color for when we get to the next set of bricks. And so the result of this is believe this is, go to breakout 7. And then if we hit a brick, since this one's blue, it should disappear. And we're playing a new sound as well, a new like death sound, just to make it clear. But notice they changed colors. So that's all we're doing. We're just taking their tier or their color and just performing a simple decrement on it, looping back. In the event that we go down a tier, we should loop back up to the highest color of the lower tier. So I'll let you look at the code for that if you want to sort of get a more low-level understanding of it, but that's sort of the high-level understanding. And the next big concept that I'd like to introduce you guys to is a particle system. And so particle systems are fairly omnipresent in video games, I would say, because they make effects that are otherwise difficult to do with simple sprite editing achievable very easily and realistically. Just like fire, for example. Things that are very organic and flowy and have a lot going on are often better represented with particle systems than they are with a simple sprite animation. So does anybody know how we might be able to, how a particle system might work underneath the hood? I think I alluded to it previously. Yes?
For example, if you have a fire, maybe draw particles in the center, and as you get away from the center, draw nice.
Yeah, so what he said was in order to make fire, for example, just spawn a bunch of particles close to the center of wherever your fire is spawning, and then outside of it, spawn fewer. That is absolutely a way to get fire to work, and also taking into consideration the travel of your particles. For example, you might spawn a ton of fire particles really densely, but then maybe they have some logic that makes them go upwards. Maybe they have a negative delta y, and then some sort of acceleration, so they sort of trail off. And then maybe sort of how to get a more realistic fire look, they travel sort of upwards and then fade away. So the way fire works, sort of thinking of things in terms of particles like that, you can achieve a lot of effects. How might we implement like smoke, for example? Same system. So we could have maybe like a timer, in our particle effect, or even a transition, because in particle systems, often you have the ability to transition colors between particles. Let's say you start off red, go to yellow, and then maybe your particle system transitions to gray or brown. And then over time, your particles are going up, they're dissipating, and they're also turning dark, they're turning brown. It sort of gives you the illusion of fire. And we won't be doing anything necessarily as complex as this in our code here, but in Breakout 8, we will be using Love's sort of integrated particle system, which is just love.graphics.new particle system. And it takes in a texture, because all particle systems need some sort of texture as their foundation. And then it needs the number of particles that it could maximally emit. And so each individual particle system can emit up to a certain instance of particles, and then the number and speed and whatnot of all those particles is ultimately the determining factor for how you can get an illusion. Back to last week's lecture, illusions, like it's not fire, it's not smoke, it's just a bunch of particles responding with colors and acceleration and stuff. But there's a lot of functions that particle system gives you in Love2D, so I'd encourage you to look at that link just to explore some of them. love2d.org/wiki/particle system. We'll be using a few of them here. I'm going to just briefly show you. So each individual brick, when it gets hit, it's going to need a particle system of its own. Because our goal is, I'll run the code for you so you can see it. So if you go to Breakout 8, and let me run it, we have the little bit of particles you saw there at the very end. And the blue ones you were probably able to see a little bit better. And then one last time. So it spawns a bunch of little particles. So can anyone tell me how they think the particles are behaving? Sort of in a nutshell, what the logic is for the particles?
Just moving outward in slightly random direction.
Yeah, slightly random. And if you look at it, you'll also notice that they tend to go downwards. So knowing that, we can probably just assume that they have an acceleration that tends towards positive y. And that's essentially all we really need to do. We spawn a bunch of particles outwards and then just set them. They have a lifetime. They last for a certain amount of time, and then they fade between two colors. In this case, we fade from red to transparent, or whatever color it is, and then after the lifetime's elapsed, it has the overall effect of sort of this glimmering gravity-based effect, but it's really just a bunch of particles that are set to spawn in different directions. Apologize for that. So we'll take a look. It's going to be in our brick class here in breakout 8. So we're going to go to brick. We have a bunch of colors that we're storing here. So if you notice, the particle systems adopt the color of whatever brick they're hitting, just so that it stays sort of congruent with what we're looking at. So we're just storing a bunch of colors here. And these are, I wouldn't worry too much about this. These are just colors from the sprite palette that we used with our sprite art. There's specific colors that are only used in that sprite. And having a palette, generally speaking, allows your art to look a little bit more cohesive when you're doing sprite art, as opposed to just picking colors willy-nilly. If you say, oh, I'm going to only use 16 or 32 colors for this palette, you'll sort of have a more cohesive look, and also a very retro look, because often hardware was limited to a certain amount of colors back in the day for older systems. So it's nice to, as an aside, and we'll look at it next week as well, looking at when you're doing your own sprite art, try to use fewer colors, and then that'll give you, it also makes it easier for you. You don't have to spend time choosing, oh, I want to have this shade of green, I wonder if it looks good. If you only have 2 shades of green or semi-shades of green to choose from, then that's all you got. You have to make do with it what you can. So what we're doing here is we're storing 5 colors from our palette. We're going to use this, and then when we trigger our, so right here, we're initializing a particle system. So P system gets love.graphics.new particle system. And then these are a few functions. So feel free to look in the wiki for how these functions actually behave, but lifetime, acceleration, and area spread just are sort of the properties that influence the way our particle systems behave. And so using whatever our current color is, we're going to set our P system's colors using setColors function. We're going to set it between 2 colors, color with 55 times tier alpha and color with 0 alpha. So the higher the tier, the brighter the particles, but they'll always fade to 0 alpha, if that makes sense. And then we'll just emit 64, and this is all in the hit function. So all we've basically done is just add this particle system trigger in our hit function, and it has the result of the behavior that we saw earlier. So any questions on particle systems or how we've used them? All right. So level 9 is the progression update. So the purpose of this update is to allow us to go from level 1 to 2 to 3 to 4 and get more interesting level generation that way. The gist of this is in our, so if you look at our start state, so all we need to really do to store a level is just to store a number. And then where do we increment the number? Or when do we increment the number, I should say?
When the table is empty, not empty when it's all false or in place, not true.
Exactly. So we set the, we increment the level, we go to the next level when all of the bricks that are in play have gotten their in play flag set to false. So we have no bricks that are in play effectively. So in our start state, so let's go ahead and look at breakout 9. So start state. We're passing in level gets 1 here. We're just going to start off. When we're going in the start state, we're just going to pass level equals 1. And then henceforth, anytime we do any state changes, from play to serve and to victory, as we'll see, victory being our new, oh, you cleared this level, here's the next level. We're just going to pass the level between them. And then in play state, the important bit of code here is on line 204. So this is just a function called check victory, which is exactly as James said. You're just going to set, we're just going to iterate over the entire table and just say, if it's in play, return false, because we're not in victory if we have any bricks that are in play, but return true if we didn't meet that condition. And so this is just a simple way for us to check whether or not we are in a victory. And so on line 88 of the same file in our play state, we're just checking to say, hey, if self.check victory after we do any brick hit, because that's when we've just set a brick to in play is false, just check victory. And if so, play a new sound, like a happy sound that we've done a victory, and then just pass everything into the new victory state that we have here. And the victory state is simply a sort of just a message state. So all it does is just renders everything as before, but it just says your current level complete, right? Self.level complete, and then press enter to serve, and it'll go back to the serve state as soon as that happens. And then here is where the actual like progression happens. When we go to the serve state, we have our level, but we want to add 1 to it. So all we need to do when we like trigger a transition into our next state, just increment level by 1 here, and also create a new map, because bricks needs to get restarted because we have a new level, self.level plus 1. And so that'll have the effect of, oh, we've gone from level 1 to 2 to 3 to 4, etc. when we go between the play state to the victory state back to the serve state. So any questions on how any of this works? Yes?
Do you have to worry about garbage collection for any of the bricks at all, or is that handled by the Love engine somehow?
Garbage collection is handled by Love, yes.
Okay.
Yeah.
So when they're not in play, when they're not referenced by anyone?
Yes, because the question was, do you have to worry about garbage collection when we are sort of clearing away the bricks and adding new bricks? The self.bricks table, this table here, it's getting assigned to a brand new table from levelmap.createMap. When there are no references to an existing table, Lua's garbage collector will trigger at whatever interval it's set to trigger and clear up all that for you dynamically, just like the same way that Java works, almost identical. Mm-hmm. Any other questions? All right. So we have progression. In the sake of speed, I won't demo, and it also takes a while just because we have to clear an entire level, then get to the next level. But that's how the behavior works. The next sort of iteration of this is high scores. And I will test to make sure whether or not this is actually working. I know I changed some stuff. Yeah, so OK, high score. Let's debug for a second. So high score state, line 38. In breakout 10. So high score state. And then the issue was attempt to index field high scores, a nil value. OK, so that means that, OK, I think I might know the issue, but it's because I transitioned to a new user that doesn't have a save file active on this. The way that we'll transition, therefore, into love.filesystem, which is breakout 10's main new things that it introduces. So writing files to your file system is done through you with love.filesystem. And there's a few things. So love automatically gives you a directory, a save directory that's pretty much hard coded. There are a few exceptions as to how to not use that directory, but it assumes that you're always using that directory. And for very few exceptions, very few exceptions, will you always use that folder. It's like app data local on Windows and application support and the name of your application on Mac. But it's a subfolder that Love has read and write access to for files on your file system. You can check whether it exists with love.filesystem.exists at some path. You can write to that path with some data, that data being a string value. And then love.filesystem.lines is an iterator, which will allow you to look over any of the data that's in a file at a given location. Yes?
I played around with pushing it to an iPhone.
Yep.
Does this work if you end up porting it to a device?
It should. We can pull that up now, actually, and see, because I know on their Love 2D, so file system. So the question was, he ported his, when you port your Love app to the iPhone, will it have the same sort of behavior if you're on an iPhone? Will it have the same sort of save directory behavior? And it looks like it's not officially on here. I know that there is a iOS port for Love 2D, or the ability to send it to Love 2D.
Yeah, directions they work. It's pretty cool.
I have to imagine, yes. It probably has some sort of, I'm not entirely familiar with how iOS handles sort of local storage, but I'm assuming that just in the way that it's been abstracted for desktops and for Android, it's also abstracted for iOS. Haven't tested it myself. I would experiment and see, actually, maybe with this code, see if you can maybe get it working with persistent high scores. I know that iOS does typically let you store a small amount of data per app in some location, a fixed location, but I'm not entirely sure what that is offhand. I can look into it more and come up with a...
But you know it works for Android.
Yeah, I mean, not from firsthand because I don't have an Android, but it has official Android support. So I'm guessing it does, but I haven't tested it. I have not tested it manually on Android to verify that. But yes, I believe because in the prior directory we were looking at, when it showed, oh, it's actually up here. This path here, this data/user/0.org.love2d.android file save, that looks to me like it's the official sort of path that data is stored on an Android device for your application. So I haven't tested it myself, but if you have an Android and you're curious, or maybe an emulator, maybe give it a shot and see if it works. Oh, and it even says here, there are various save locations, and if they don't work, you can see what the actual location is with this function here, the love.filesystem.getSave directory. That may work on iOS as well, so I'd be curious to hear about whether that actually works on that. But yeah, so that's the gist. Using the love.filesystem abstraction lets us read and write files. We can then just paste, or we can just save whatever data we want anywhere within that directory. We can just create files in there and then use those to store our, sort of game worlds or character profiles or whatnot. How would we maybe go about implementing sort of like a high score list? So I'll look, there's a picture here. So we have 10 scores. We'll assume that's fixed. Each of the scores has a name, and then each of the scores has an actual score. So all we really need to do is just store ultimately the names and then the scores.
So you just use an array, and then you can just sort it by that score.
So we'll use an array. Their response was we'll use an array and sort it by that score.
Table in this case, right?
Yeah, essentially that's exactly it. We're just going to keep a score table, and each table is going to have a subtable. Each of those entries, 1 through 10, is just going to have a name and a score. And then once we're done with our application, we'll just use love.filesystem.write. We have to convert all of those into a string, right? Because we can't just take a table and then spit that out into a file. We have to actually make it into some form that we can save and then reload back in somehow. What would be the most efficient way, do you think, or a way we could do this? Probably just a new line separated list. The way that I've done it in this application is just names and then new line, score, new line, name, new line, score, 10, so 20 rows. And that gets the job done. Assuming that you don't tamper with the file, then everything should work. And you can write additional code as well to say, oh, if there's a score that's all garbled or we don't have enough scores, then probably should render it accordingly. My code does something similar to this, but not entirely. The relevant code, and I'm going to sort of just glaze over it. If we're looking at, this is breakout 11, right? Yeah. Oh, no, this is breakout 10. So in breakout 10, we have to load all the high scores in main.lua, which is here. So set identity to breakout. We're going to create a folder called breakout that we can save and read files to and from. If it doesn't exist, then just create them. In this case, I'm just seeding CTO, my initials, and then I times 1,000, so 10,000 down to 1,000. Just very simple data. Writing it to a file called breakout.lst. It can be whatever you want. All we're doing is reading the lines from the data, or from the file. And then this is if it doesn't exist. And then if it does exist, then we're going to iterate over it with love.filesystem.lines, which will take a file and then it'll just split it on new lines basically and give you an iterator over all those lines. So we can just say, okay, if it's a name, which means that if it's one or 3 or 5 or 7 in the list, then set the name to, and we're using string.sub just in case they write some long name or some long name gets, they can't do it through our game, but if it gets written to the file as some long name, it should get truncated to 3 characters so we can display it appropriately. And then otherwise, if we're not on a name line, if we're on like an odd line, then we should, or an even line, we should consider that a score and just like use toNumber because, right, we're using string data. And if we try to assign, like do any sort of comparisons numerically on the string data, which we will have to do to compare high scores, it's not going to work because it's going to see that they're strings. So we use toNumber here, just a simple Lua function, and then that's it. And then we just return scores. And then I'll sort out what the it's causing the issue, and then push that to the repo ASAP. But that has the effect of us being able to actually load all of our high scores and display them at the start of the game. It doesn't take care of being able to actually input our score. And so we can do this with breakout 11, which you can see if you run the repo. And you can, to test, just assign your initial score to some value like 10,000 or 20,000, and then just lose on purpose, and you'll get a sense of how it actually works. But essentially, it's just arcade style. You know, you had only 3 characters you could input your name. So does anybody have any idea as to how we are sort of storing this, or can pitch an idea? So we have 3 characters. And we want to, ideally, if let's say I want to go to C on the first one, and let's say I press up twice, so I get to C. How is it going from A to C? You could just render, oh, I want to render the character A, the character A, the character A, but that's not really going to, how is it going to know when you want to go to B or to C or to D?
How do you go, when you press up, how does it know to go to B, and down to go to down one? Again, you could just do a table and iterate through it and number the letters.
The pitch was you could create a table with all of the characters and iterate through it. You absolutely could do that. It's a little bit bulky. That might be what, actually, that's probably not how arcade systems did it back in the day. Because the way that we're going to do it here in breakout 11, or is it breakout 11? Yes, breakout 11, is I added a new state called enter high score state. And if you recall, CS50 teaches this, but all sort of characters at the end of the day are just numbers. ASCII, in this case, 65, if you recall, is capital A. So all we need to do is just draw out whatever that character cast to a string is, or a character. And we do that simply down here in the draw function. If we do string.char at chars3, all that has the effect of doing is just taking that number and then converting it to a character. So all we need to do then is what? When we want to, we'll go from A to B, B to C, C to D. Exactly. But then what happens if we're at A and we want to go down? We would. So if we're at A, then we probably, if we press downward and we want to go to Z, the logic is in here. But if, once we've incremented our code and it's greater than 90, which is Z, then we should set it back to 65. We'll loop back to A. And same thing here. If we press down and we're at A, we probably got to go back up to Z, so we'll just set it to 90. So a simple loop back logic, and we just draw it, we highlight, and then once we've done that, the user presses enter, we transition to the high score state, actually. Because this state should only trigger if they entered a new high score, which means that we need to check in the victory state, or not the victory state, but rather in the game over state, whether or not their score is higher than any of the stores in some sort of quote-unquote global scores table. And then how do we think we're passing the scores back and forth now? Does anybody recall how we're keeping track of app state?
We were passing it every time we did these. So what is it? The state.
Yep, in the change function. So all we need to do is just keep track of load our high scores at the beginning of the game, pass them all the way down the line. And then finally, and we could also load them in our enter high score state, but we need to keep track of what our high scores are in the game over state so that we know, oh, I got a high score. Let's, instead of transitioning back to the start state, let's transition to the enter high score state so the user can add their high score to the list. And then once they've entered their high score, whoops, which is here, we'll just write it to this file again. We compile a score string, which just takes name and score of our scores. We take whatever score that we were at. That's what we look through our scores table backwards, and when we find a score that's higher or that's lower than ours, we just keep track of that index until we get to one that's higher than ours. In which case, the 1 plus 1, that index plus 1, is what we should then overwrite. And so we shift all the other ones below accordingly. And we do that in this class, if curious. And so I'm just going to breeze through the last couple. The paddle select update is just kind of a fluffy state that lets us add a element of sort of like user selection to our game. In our paddle select state here, we transition immediately. Instead of going to the serve state or play state now, we're going to go from start to paddle select when we hit start game. So we're going to go to, and then the paddle select class itself. Current paddle gets 1, and then all it essentially is us drawing 2 arrows here. And so if we're at number 1, in this case I think we're at number 3, then both of these arrows will be completely opaque, but if we're on the left or the right edge, they should darken to say to us, oh, we can't move left or right anymore because we're at either index 1 or 4 or 5, and there's only that many colors. And then render whatever that color variable is, using the quads table that we had before of the different tables, and then just instructions. And then from there is where we'll end up transitioning to the serve state rather than going to the serve state from the start state. And all the code in that is here. We have sound effects playing, and then making sure that we also play a different sound effect based upon whether they're at the left or the right edge. If they're on the left edge and they try to go left, it should play like a sound that sort of sounds a little rougher to let them know that they can't go left, and the opposite for the right edge. And then once that's all done, once they press enter on whatever paddle they want, they're going to get the paddle. They're going to instantiate a paddle, pass that into the serve state, and we're going to take current paddle from the state, which is whatever value they got by scrolling between all the different paddles. And then the last update, which is my favorite part of most every lecture, I think, is the music update. And all that really is just music set play in main.lua, and then set looping to true. And then we have a game. And this is our paddle select. So notice the arrows are semi-opaque on the left and the right. And it's kind of hard to hear, but when I press right now, it's kind of like there's a bit of a rougher sound. We choose red. We go to level 1. We've transitioned to the serve state from the paddle select state, and then we just play the game as normal. And that's basically all there is to it. And there's a couple of features we didn't have time to really go over, like making sure we recover HP if a certain amount of points have been elapsed. But I encourage you to look into that. When you trigger a hit, there's some logic in the play state to say, oh, if we've gone over our current recovery threshold, let's add 1 heart to the player, just to keep them playing, just to reward them for their high score. Next time, we'll cover a few concepts. So basic shaders. Shaders are like little programs you can run on your graphics card to do fancy effects, but we won't go into too much detail. Anonymous functions. We've seen a lot of anonymous functions in Lua in the context of Love. They're just functions without a name, and you can just use them as function arguments and do all sorts of cool stuff with them. We'll use them for callbacks in next week when we do things like tweening, which is taking some value and making it interpolate over time to some other thing. Because right now we've basically just been updating things based on velocity, but we haven't really done anything based on time. So we'll take a look at that in more detail next week with a library called Timer, which is really fantastic. Lets you time things and then chain things together. We'll be covering the game Match 3, if familiar. It's basically Candy Crush. We'll be using a different tile set, but it's the same idea. and we'll have to calculate how to actually find out whether we've gotten a match in the grid, our tile grid, and then shift the blocks accordingly and do all the other logic, add score. And then basically, since it's so fundamental to Candy Crush and games of its nature, we will have to cover how to sort of generate these maps procedurally to have tiles that are laid out in a dynamic way, and also in a way that doesn't start off with any matches, because then that wouldn't make any sense, because the matches have to resolve. And then we'll take a little time, if we have the time next week, to talk about sprite art again and palettes, and maybe I'll show you guys how to sort of convert images from one palette to another in like a program that I use, Sprite, but you can do this in any sort of large photo editing software. And then assignment 2 is a couple of extensions to assignment or to Breakout. So if you noticed in the sheet, there were a few little sprites here at the bottom. So let me get rid of the quad outlines. So these little things down here are, I'm assuming they're meant to be power-ups. They look like power-ups, but the goal of the pset is to implement a power-up. And the power-up is going to be such that when you grab it, you'll get 2 additional balls, or however many you want actually, that will spawn in addition to your 1 and detect collisions on their own. So you'll have several, and they'll score points for you. And of course, only when the last ball comes below the surface of the screen should you trigger a game over. And then I want you to add, and this will also be more detailed in the spec, but I would like you to add growing and shrinking to the paddle. So currently we have like 4 different sizes of paddle, but we're not using them. So it would be nice if when we gain enough points, or we lose points, or not points, but lives rather, we increase or decrease the size of the paddle accordingly, just to introduce another level of challenge and or lack of challenge. And then finally, one last part, which is in the sprite sheet as well. There's a key block here and a key power up here. So sort of let the power up come, pick the power up up with your paddle, and then only when you have that power up should you be able to break the block with the key. And you should take this into consideration when generating your levels as well, so you'll have to also get your hands dirty with the level maker. But all in all, that was Breakout. So I'll see you guys next time. Thank you.